The NASA Plankton Aerosol Cloud and Ocean Ecosystem Mission has been in orbit for just a few years now. Here's a few highlights of some of the exciting observations PACE has made since then and continues to make every day. In some cases, these are first-ever measurements, things that have not been observed from space before. Others are new and unexpected. PACE, as its name suggests, is an inherently multidisciplinary mission. Not only can we observe the atmosphere, ocean, and land surfaces from PACE, but connections can be made between these different observations. Let's start with an example of how PACE observes wildfires and smoke. This is a large-scale true color image, and we can see the very destructive fires that occurred in Southern California in January of 2025. What we're looking at in this image are smoke plumes, and you can see them blowing off from the Los Angeles region out over the ocean. But we can also look at the impact of these fires on the surface itself. So PACE can measure the relative burn severity from these fires. We can also look at the smoke from those fires as it's transported away from the region. So smoke is a particle, in other words, an aerosol. An aerosol is a terminology that scientists use to describe any sort of particulate matter in the atmosphere, which includes smoke. So what we see in this image is aerosol optical depth. This is a measure of how much aerosols are present in the entire atmospheric column, meaning from the surface to the top of the atmosphere. If you look to the top left, you can see the Palisades and Eaton wildfire smoke plume as it's blowing out over the ocean. If you look more towards the middle of the image, you can see another plume, and this is coming from Baja California. The question is that also smoke? We believe it's not. We believe this is dust, because of the other measurements we're making with PACE that give more clues as to what's present. So one clue is to look at the light absorption of the aerosols. Dark particles, very absorbing particles, are usually associated with smoke, whereas brighter particles can be dust or other types of particles in the atmosphere. Another piece of information is the aerosol size. Smoke particles tend to be very small relative to dust particles, which are larger. Now let's move to another event that's crucial to monitor. This is from the OCI sensor on PACE, and it's an indication of cyanobacteria in the Great Lakes and nearby areas. Some cyanobacteria are toxic. That means that they affect drinking water, and through that, humans and other organisms in and around the Great Lakes. This animation is from several weeks over the summer of 2024, and we can see a couple of regions in the Great Lakes that are affected by cyanobacteria. So now let's zoom out a bit and look at aerosols in a different way. So now we're looking at the aerosol index, and this is really great for exploring large-scale phenomena from aerosols, and it relies on the sensitivity of the OCI sensor to the ultraviolet part of the spectrum. One of the great sources of aerosols globally is the Saharan Desert. So what we're looking at in this animation here is some of that dust from the Saharan Desert blowing west over the Atlantic Ocean. If we look to the north, we can see another plume, and this is related to wildfire smoke from fires in Canada and the United States. And these smoke particles are transported out across the Atlantic Ocean to the east, sort of in a circulation pattern, dust moving west, smoke moving east. So now let's move to one of the great strengths of the OCI sensor, which is to identify phytoplankton type in the ocean. Right now, we're visualizing pico-eukaryotes, which are a type of small algae that really thrive in coastal areas where there are more nutrients and the conditions are right for their growth. Next is Prochlorococcus. So they thrive in conditions of low nutrient loads. And so you can see that they are dispersed much farther from the shore out in the middle of circulating ocean gyres. And finally, Synechococcus is a type of algae that thrives in a sort of borderline between high and low nutrient areas. So each of these are interesting to consider as different ecosystems in the ocean. It's almost like on land we have grasslands and we have forests, and they're that way because of how much water is there, how much nutrients are there, and it's the same thing in the oceans. And what's very important in the oceans is that these areas move. Forests don't move quickly, but these regions do. And this is something that we can track with the PACE mission. So now let's move to the other side of the world, off the coast of Russia. What we're visualizing is another class of phytoplankton, diatoms. Diatoms, like all types of phytoplankton, follow ocean currents, and you can see the swirls and interesting patterns here that are associated with how water is moving in the area. So this particular class of phytoplankton is important because they transfer carbon into the ocean. This interacts with ecosystems and ultimately fisheries. Now let's move to South Australia, where there's another type of harmful algal bloom in progress. This is not cyanobacteria. These are larger organisms, but just like cyanobacteria, they create harmful compounds in the water which can adversely affect humans. So OCI is sensitive to this type of harmful algal bloom by looking at the combination of backscattered light and fluorescence of light. In other words, using the optical properties of particles in the ocean, we can determine what's there and if it's dangerous. So now let's look at clouds. One of the aspects of PACE is that two of the sensors on PACE are multi-angle, meaning that they observe the Earth from different geometries. What we can do with that is reconstruct the 3D nature of clouds, in this case from the HARP-2 instrument. So this is important for understanding climate, weather, and of course aviation. This is a product that's in development. We're making use of new machine learning tools so that we can produce this product globally. So that's not the only measurements of clouds that we can make from PACE. If we move to the west off the coast of California, we see a very persistent cloud deck of a type of clouds called marine stratocumulus clouds. So these are low-level clouds that are persistent off the coast of California. If you look at them, you can see little streaks through here. These streaks are due to the presence of humans, specifically shipping throughout the area. We call them ship tracks because the emissions from ships interact with clouds and change their nature. In this image, a true color image, we can see how they're brighter because of this. But we can also look at the cloud droplet size distribution, how big or small the cloud droplets are. Another PACE product is the cloud droplet effective radius. It's sort of like the average size of the particles in the cloud. You can see here a change in the size of the cloud droplets, indicating the presence of ships. Now let's focus our attention on OCI's ability to monitor land surfaces, which is something that was not in the original plan of PACE. So OCI is sensitive to concentrations of leaf pigments around the globe. This advances our ability to measure things like forest and crop health, and we can do so globally. So here we can see the advance of fall colors as we transition from a chlorophyll or green pigment dominated state to other pigments which are associated with the yellows and reds that we expect to see in fall colors. So those are just a few examples of the measurements that we're making from PACE. The highlighted scenes are specific examples, but these measurements are made globally throughout the Earth. Some of the products are still in development, but others are free and available to the public, including scientists, decision makers, or anybody who's interested in exploring the connections between different elements of our changing planet Earth.